Hi everyone, in today's video we're going to do a speed test for JAX. If you don't have time to watch this video, here is a summary. It's ridiculously fast. You should start using it. So here is the notebook I'm working on. First, I would like to acknowledge the help of these 4 references. The first 2 are articles from JAX documentation, and the second 2 I borrowed code from these references. Before I start, can we just take a moment to appreciate how good JAX documentation is? I started coding in Python in 2018, and at the time I was coming from MATLAB. MATLAB documentation were great, but that was understandable because MATLAB is a commercial product and they have their own customer support to create great documentation. But after learning Python, I accepted the fact that documentation are not always great, and I have to rely on the community questions and answers to fill in the gaps. But this is not the case with JAX documentation. The JAX documentation are well written. It's clearly written by researchers with examples. Each page of the documentation is self-contained, and you can open it in Colab. So for example, JAX the sharp bits. This is it's just like a story with examples, and it's self-contained. I don't have to go to Stack Overflow to see how can I use the function. What I hate about documentation in open source libraries, they keep adding notes about each specific case. And at the end, this page of documentation will be just a list of notes for each specific case. So a page of the documentation loses its storytelling feature, which doesn't hook the reader to the documentation, and you have to look somewhere else for examples or for use cases. So to the JAX team, good on you guys, keep it up. You're doing great service to the open source community. So here I'm importing libraries, I'm setting plots to dark background, and I'm creating the colors for the plots, and I'm initializing an empty list just to keep the timing for each run. These are hyperparameters for the data loaders and to load the CFA10 dataset. Here I created a 2-dimensional toy dataset. I already explained this example in my video, a simple neural net in JAX. So if you're interested, you can check it out. I'll link it in the description. 10,000 points. These are 2-dimensional points. And this how do they look like? I'm splitting the data to 80% training and 20% testing. I'm loading these data sets using the batch size, which I set to 128. I'm loading these data sets into data loader, that's 1 for training and 1 for testing. Here I'm defining a multi-layer perceptron classifier with 3 layers: input layer, hidden layer, and output layer. So this is how the multi-layer perceptron looks like. I'm sending an input of 1 batch from the training data set, 128 by 2, 128 points in 2 dimensions. In the hidden layer, they will be multiplied with 10 neurons to create the weights, which is 128 by 10. Here in the hidden layer, it will be passed through a reload function here, but I didn't put it in the notes just to save space. This 2-dimensional array will be sent to the output layer to be multiplied by the weights of the output layer to create the predictions. I'm initializing the optimizer to optax.atom with a learning rate of 0.01, and I'm initializing the model with a random array of this size. Here I'm creating the train state required by flax to train the model. These are the training functions. I will send the train loader to a function called train model. Train model will call a function called train epoch, which will send the batch to apply model, update model, and it will loop for all batches. Once I finish all batches, I will go for all epochs all over again to train epoch. Then I will train the batches. Apply model and update model will be applied for each batch, but train epoch will be applied once for every epoch. So here is apply model, update model, train epoch, and train model. What I'm jitting apply model and update model. So I'm including JAX.JIT before these 2 functions, because this is what are the real computations happen in apply model and update model. If I call train model with the model state that I initialized randomly, and the train data loader and number of epochs is 1, but I am calling time it, then I'm specifying the parameter O just to save the timing output into a variable called function time. So what time it will do, it will run 1 epoch, which is basically this function. It will run it for 7 times and will retain the mean and standard deviation for the running time. So it took 65.7 milliseconds, and the standard deviation is 1.73. Then I'm appending the mean of the function timings and the standard deviation to the timing list that I initialized at the beginning of the notebook. So this was the JIT training for multi-layer perceptron for 10,000 two-dimensional points divided into batches. Each batch has a size of 128 points. Now let's do unjitted training. Unjitted training, what I have done, I copied the same functions, but I changed the name to apply model no JIT and update model no JIT, train epoch no JIT, and train model no JIT. Then I removed JAX.JIT from all of these functions. Now I'm calling train model no JIT, then I'm timing the running time for one epoch. On average, it took 2.36 seconds, and the standard deviation is 24.5 milliseconds. So no JIT, it took 2 seconds, but with JIT, it took 65 milliseconds. Then I'm appending the mean of the timings and the standard deviation of the timings to the timing list. Here I'm loading CIFAR10 dataset from torchvision to JAX. I already explained this loading process in my video about convolutional neural net in JAX. I'll link it in the description. You can check it out. I'm importing train dataset and a test dataset, and I'm splitting the train into train and validation splits. And I'm loading these into a train data loader, validation data loader, and test data loader. And I'm performing data augmentation in the train images. And I'm just converting the test images into NumPy to be accepted by JAX. Here is the convolutional neural net architecture. First, it will pass through a convolutional layer with 32 filters. It will pass a ReLU function, then average pooling, another convolutional layer with 64 filters, and then a ReLU function, average pooling. Then we will flatten the height, width, and depth of the images to pass it through a linear layer, non-linearity, then a final linear layer to determine the class of the image. So here I'm initializing the model to CNN, and I'm setting the optimizer to optax.atom, and I'm initializing the model with this random array. The JIT training for CNN, I'm using the same functions that we talked before earlier, basically these functions. Here, apply model, JAX.JIT, apply model, JAX.JIT, update model, train epoch, and train model. So I'm calling these for the train loader of CIFAR10 dataset with one epoch, and I'm timing that. For 7 runs, it took 7.45 seconds, and the standard deviation was 19.1 milliseconds. But training with no JIT, it took 29 seconds. Can you see the difference? So we went from 7.5 all the way to 30 seconds. So here is just to visualize that difference between the running time with JIT and with no JIT. So this is the running time for the two-dimensional data. With no JIT, we almost took 2.5 seconds. But with JIT, it was 0.2 seconds. And to train the convolutional neural net, it took us almost 30 seconds with no JIT. But with JIT, it took us 7.5 seconds. So this is a huge reduction in running time. But how JAX is doing that? How does it achieve this reduction? If you check this page in JAX documentation, it's called just-in-time compilation with JAX. So they have this function for scaled exponential linear unit. They define it here. And when they time it with no JIT, it was 2.05 milliseconds. But when they JITted this function, the running time went down to 150 microseconds. Here's what just happened. We defined CeloJIT as the compiled version of Celo. We called CeloJIT once on X. They're talking about this call. Here they call it a warm-up. We didn't do that in our notebook. I just included that in the running time. And even with including that, JIT was way faster than no JIT functions. So this is where JAX does its tracing. It needs to have some inputs to wrap in traces. After all, the JAXPR is then compiled using XLA into very efficient code optimized for your GPU or TPU. Finally, the compiled code is executed to satisfy the call. And here is the point. Subsequent calls to CeloJIT will use the compiled code directly, skipping the Python implementation entirely. Once JAX do its tracing on the function, apply model and update model in our case, once it does the tracing for the first time, for the first batch, all the subsequent calls for the rest of the batches was done using the optimized version of the code. It didn't use the Python original code, it used the optimized version of the code. But when we remove JAX.JIT, JAX has no option but to use the native Python implementation. That was not efficient. This causes the delay. These subsequent calls were not optimized, where when we use the JIT function, we call the optimized code. To understand more about JAX optimized behavior, here is a great answer in Stack Overflow from one of the developers in JAX team. So he says, JAX does cache the JAXPR and compile artifact for each compatible call of the function. This compatibility is determined via the cache key, which contains the shape and the type of array arguments, as well as the hash of any static argument and some additional information such as global flags that they may affect the computation. Anytime something in the cache key changes, it results in a new tracing and compilation of the function. You can see this by printing the cache size of the compiled function. To make the most out of the JAX optimization, make the cache size as small as possible, which means that you are not changing the cache key. You are keeping the shape of the arrays, the data type of the arrays, the same for all the calls for the optimized function. Otherwise, if you change the shape of the array or the data type of the array, JAX will have to trace and compile a new version of code, and this will cause the delay. So this is really the key in JAX optimization, and just letting JAX compile for once, and then just use that optimized code for all the subsequent computations. This will result in a really fast code. So let's check the cache size variable in our code. So this is the same notebook that we worked on. Here are the optimized functions: apply model, update model. I called apply model and I printed the cache size for apply model. The cache size was 0 because it wasn't called yet. Then for all batches in the data loader, I'm taking the images, the labels, and I'm passing the model state, batch image, batch labels to the apply model, and I'm printing the cache size. The cache size changes to 1 with the first batch in the training loader. It was 1 for all batches at the trail loader except for the last batch. How does that happen? Why did we have to trace and compile apply model again? What causes that? What causes that is the last batch in the train loader doesn't have 128 samples. It has less samples than all the batches in the train loader. So for all the batches, we have 128 samples. So we didn't change the array, and the cache size kept the same. So we're calling the same optimized function over and over again, except for the last batch when we change the shape of the array from 128 by 2 to something less than 128 by 2. So then we trace the apply model function and we call it again. To avoid this change here and keep using the same optimized call for the function, you can drop the last batch, which has different size than all other batches. To see the JAXPR translation for our apply model function, we used JAX.makeJAXPR to apply model with the call of model state, batch images, batch labels for the first batch in the train data loader, and it got this JAXPR function. So it's very hard to read here in the notebook, so I have to paste it in VS Code just to make it easy to visualize. So here is the translated function in JAXPR. I'm not going through all of this because it's very, very long, but let's check this part here. This performs multiplication between BK and Y. The size of BK is 128 by 2, and the size of Y is 2 by 10. This is the multiplication of the input to the weights of the hidden layer. So this is BK, which is 128 by 2, BK 128 by 2, and this is Y, 2 by 10. Y here, 2 by 10. So this line here will perform multiplication between BK and Y, between the input of the hidden layer and the weights of the hidden layer, and it will save that into a variable called PM of size 128 by 10, which is this n-dimensional array here. Then it will add PM to Bn. This is adding the bias. Then it will apply a ReLU function. Then again it will perform multiplication between BP, which is of size 128 by 10, and BA, which is of size 10 by 2. This line here is equivalent to the last layer here, 128 by 10 multiplied by 10 by 2. It will result in 128 by 2. It's 128 by 2. And it will add the bias, and it will apply softmax at the end. So my final remarks on JAX, just-in-time compilation. At the end, neural net relies on mini-batch training, which is basically running the same n-dimensional array over and over again. JAX, by doing JAXPR translation, it optimizes the function, the training function. It will just discard the native Python implementation and just keep calling the optimized Python function, because it's the same size, the same data type, but with different input each time. It will make the neural net training very fast, as we can see here for the multi-layer perceptron and convolution neural net. One final note about PyTorch. PyTorch is not slow. Yeah, don't think that if you run on PyTorch you will get this slow training time. No, PyTorch is very optimized. But the thing is, PyTorch does not explain its optimization. I don't know where the PyTorch efficiency came from. But in JAX, everything is explained in detail. They even give you the function to translate to JAXPR and to investigate the code yourself, the intermediate code, the optimized code. So PyTorch is not slow. It's very fast and optimized library for training neural nets. But I don't know how it's doing its optimization. Is it through intermediate translation, just like JAX, using some other language? I don't know, but it's really optimized. But what I like about JAX, it's really open about its optimization. You can call the intermediate code. You can look at it. You can investigate. This gives you more tools as a developer to optimize your code and just to keep calling the optimized version and avoid the translation to JAXPR. So that's it, guys, for today's video. I hope you find it useful. If you like this video, please like and subscribe. By the way, you can find a link to the notebook I'm working on in the description below. Thanks for watching. Bye.